Okay, hi everyone. Welcome to November's Friends of Lunar Volatiles. I know we skipped October because of DPS, and this will probably be the last call of the year. I don't think we'll do a December call given AGU and holidays and everything. So to round out the year, we have Micah Schaible, who is going to be talking about some experimental work that he's done on solar wind sputtering from ice-covered regolith analogs. So Micah, I will hand it over to you and let you introduce yourself a little bit more if you'd like, and then I'll let you take it away. And it looks like everyone else has remembered to mute themselves if you're not speaking. And if folks have questions, do you want us to leave them until the end or?
No, people can definitely just jump in if they have any questions. I'm not sure I've got enough content here to fill the whole hour. I'm sure I could talk until the hour was up, but no, I would prefer if people would jump in and we could just kind of go based on that.
All right, sounds good. And looks like we can see you as well. So yeah,
Yeah,
take it away
I think
whenever
it's
you're
working.
ready.
All right. Let me go to the share screen. There we go. Full screen it.
Yeah,
And
looks good.
hide floating media controls. Okay. Well, thanks, Parvati, for giving me this opportunity to speak with this group. Been following Lunar Volatiles for a number of years. Did some work back in grad school looking at OH formation in hydrogen irradiated silicates. And then went off with my advisor and did a little bit of work looking at solar wind sputtering, the formation of exospheres, and particularly secondary ions. So I am now a civil servant scientist at NASA Goddard Space Flight Center. I've got about 15 years of experience doing experimental analog work in laboratory settings, looking at radiation interactions with a wide variety of different analog samples spanning materials from the moon to Mercury to asteroids, a little bit of icy bodies, and really looking at what are the both chemical and physical effects of that radiation on the surfaces of airless bodies. So the work that I am wanting to talk about today is looking at the potential of solar wind sputtered secondary ions to produce an observable signal for trace abundances of water on the moon. And so this work grew out of some of that sputtering calculations that I did during grad school, and I collaborated with Kevin Hand at the Jet Propulsion Laboratory, whose lab I used to take a lot of these measurements. And so the problem or the scenario that we're thinking about in this work is using the solar wind ions as a source of primary ions, which then produce secondaries on the surfaces of airless bodies. And so that solar wind is predominantly the KeV hydrogen and helium component, interacts with the lunar soil and produces sputtering. So the sputtered particles are predominantly neutrals. And so for the lunar soil, which has iron, silicon, aluminum, titanium, magnesium, you see all of those are sputtered in relative abundance to their compositional abundance in the surface. But some small fraction of those sputtered particles leave as secondary ions. And so those ions are what we're really interested in with this work today. So those secondary ions, they are representative of the surface composition. But then the other side of this is that we can also detect the presence of adsorbed volatile species, for example, water, through its secondary ion signature as well. And so the questions that we're asking with this work is, can the solar wind produce sufficiently high abundances of sputtered secondary ions to allow for observation and detection, in particular of these trace elemental species and water? So solar wind interacts with airless bodies, small bodies throughout the solar system. Any body that doesn't have an appreciable atmosphere or magnetosphere to deflect the incoming solar wind ions is susceptible to sputtering from both solar wind and magnetospheric ion radiation of their surfaces. So the way that that works is the solar wind comes in, it smacks into the surface atomic layers, produces a collision cascade, which then transfers the energy of the primary ion to the target atoms. The interaction of that primary ion with the target atoms, the surface atomic layers here, can transiently ionize certain species, and if those species are near enough to the surface, they can leave in the ionized state, and those are the sputtered secondary ions. Those sputtered secondary ions can be detected with very low backgrounds and high sensitivities using secondary ion mass spectrometry, which I'll talk about a little bit more. And the reason for that this is a potentially powerful and useful technique for the lunar surface is that when we're thinking about detecting water species in particular, that's typically done using mass spectrometry with a filament ionization source. And so in order to be able to detect those desorbed water molecules, you have to first ionize them. The way that that's done in typical mass spectrometry is through heating of a filament, emission of electrons, and colliding those electrons with the background gas molecules to then ionize them and be able to sweep them up and detect them with the instrument. The issue with using a heated filament to detect water is that water is one of the primary outgassing gases that come from heating up a filament. So as soon as you turn on that filament, it starts degassing water from the walls, from the filament itself, from all of the parts that are exposed to the heating of the filament, and that can overwhelm the signal for trace volatile species such as water. And so the secondary ion measurements do not require that preliminary ionization step. And so the abundance of sputtered secondaries is dependent on the sputtering rates, how many of these secondary ions are coming off the surface for a given incident ion flux, and what is the instrument collection area. So how many what is the region of surface that is being observed by our instrument. So the questions that we're really asking here are, how do the elemental yields differ for sputtered neutral and ion species? What is the secondary ion yield dependence on the amount of water that is absorbed onto regolith grains? And then in order to determine how those ions are coming off the surface and what is their detectability, we also want to know what is the ejected secondary ion energy distributions. So the experiment that I'm going to be talking about is done with primary ion sputtering using solar wind analog ions and detecting the sputtered secondaries using secondary ion mass spectrometry. And the results of these measurements give us what are the total and secondary ion fluxes sputtered by solar wind from these ice-covered regoliths. And so the results that I'll be talking about today were done on two different substrates, an electronic grade amorphous silicon, SiO2, and a ilmenite mineral substrate. The electronic grade SiO2 has a very, very flat surface, whereas the ilmenite sample was roughed up using some sandpaper, and so it's got a much rougher surface. The measurements were acquired first at room temperature, then after cooling the samples to 100 K and depositing about 50 monolayers of D2O onto the surface. Radiations were done to fluences of about 10 to the 16 H plus per centimeter squared. And then we compared the SIM spectra before and after the deposition and irradiation to see if there was any changes in the surface composition resulting from the water deposition and irradiation.
Quick question.
Yep.
Hey, Micah, it's Michael. When you say that you deposited 50 monolayers, is that like this isn't a QCM, or is this a QCM, or is that more of like a 50 Langmuirs?
More of like a 50 Langmuir. So what we did not have a QCM to do the background deposition. What we did is it used a small tube that was directed direct onto the sample. And so in order to determine what the thickness was, we basically opened up the dosing tube at room temperature. So when nothing was sticking to the sample, and determined from that what a given opening level of the leak valve produce in terms of the background gas pressure. Then after we cooled it down and we opened it up, we actually didn't see much of an increase in the background pressure. So we were able to determine that the vast majority of those leaked water molecules were in fact sticking to the surface.
Yeah, and was this Radamathes, Kevin's chamber?
That's correct.
Okay, thanks.
All right, so we took the SIMS measurements at multiple temperatures and dosing conditions. And this is the chamber that was used. And so this is the radiation simulation chamber at JPL. As Michael just said, it is colloquially known as the Radamathes chamber. And it consists of a Haydn quadrupole mass spectrometer, 0 to 5 keV ion gun that we used for the hydrogen irradiations, an electron neutralizer, which I will say for these experiments was actually not working. And so that is, well, we get into that a little bit, but that was also on there. And then we would be able to characterize our beam using the phosphor screen. And so after focusing and positioning our ion beam, we were able to achieve about a 3 millimeter diameter beam spot size shown here on the phosphor screen. In order to determine what our incident beam flux was, we would then translate our sample holder without changing the incident beam parameters and impact that beam onto a aluminum current post to measure what is the incident ion beam flux onto that. We would then further translate the sample holder to the amorphous SiO2, the ilmenite, or I do have some data on a pyrite, although I'm not going to talk about it today. We did have a couple other samples in here, an olivine and an anorthite, but because the electron neutralizer wasn't working, we were not able to obtain data from these two samples. And so what that implies is that the amorphous SiO2, the ilmenite, and the pyrite were all conductive enough to maintain surface neutrality, whereas the olivine and the ilmenite samples charged up the surfaces due to the impacting ions, and we weren't able to get any signal from those. So then we would, the whole sample arm, sample holder arm was connected to a cryogenic sample holder or a cryogenic refrigerator, and we were able to cool it down so that the temperature measured on the post was about 100 K. And as we'll see, we're able to verify that the water was definitely sticking onto these samples and fully covering them. So this is what the spectra look like for the amorphous SiO2. In the green, we have the SIMS spectra measured before cooling or depositing any water. So this is the room temperature before spectra. And we see that that spectra is dominated by silicon ion. And so Si plus is the main sputtered secondary ion from that room temperature SiO2. although we do see some substantial abundances of SiH, a hydrated Si, and SiOH, which was actually the second largest signal in that preliminary room temperature spectra. And so we see that even in these room temperature SIM spectra, we can see a recombination of the incident hydrogen ion with the silicon, which persists after sputtering from the surface. Then after cooling down and depositing the water in the black, we see our freshly dosed sample. And this shows that the sputtered ion spectra consists entirely of water cluster ions. And so that means we've completely obscured the underlying substrate. No secondary ions can come from the Si in this freshly dosed sample. And so we see exclusively these water cluster ions, which are dominated by the D2OH plus and the D2OD plus, with smaller abundances of the 2 water molecule containing clusters as well. So we do see that there is some residual H2O in the chamber. That's just the background deposition, so it's not pure D2O desorption. And then after sputtering for a while in the red curve, we see that we eventually reveal the substrate, and the substrate ions again grow to dominate the secondary ion spectra. Interestingly, we see that when we irradiate the partially covered silicon substrate, which has been partially covered in these D2O molecules, we see changes in the secondary ion spectra compared to the room temperature, where instead of being dominated solely by the hydrated, we also see deuterated secondary ion species coming off. And so we see that compared to the room temperature spectra, there's a significant increase in the sputtered ion intensity of SiD+, and in particular, a very significant increase in the sputtered intensity of SiOD+. And so comparing that to the room temperature spectra, we see that there's a lot of SiOD+ being formed in that deposited and irradiated SiO2 sample. When we look at how that secondary ion spectra changes as a function of the incident ion fluence, we see that there is at first a slight decrease and then a slow increase in the sputtered water signal. And so these solid lines all represent different water ions, water group ions. And so the most dominant water group ions, again, are the D2OD+ and the D2OH+. And we see that those reach a peak, as do all of the other water group ions, just as those substrate ions are beginning to grow in. And so then the substrate ions are shown by the dashed lines in the Si containing ions. So we see that just as those secondary ion peaks from the substrate are growing in, the water group ions pass through a maximum and then begin to decay with first order desorption kinetics. We could have kept irradiating out, and we'd see that eventually all of these water ions would go away. We stopped the experiment just due to time constraints, but we do see that as the substrate signal goes in, we are indeed removing the residual water from the surface. When we look at the derivative of the secondary ion intensities as a function of fluence, we see that, again, those water group signals are peaking just as the silicate substrate ion peaks are growing in. So this was done for an approximately 10 monolayer water thickness at a relatively low incident beam flux. So the total flux being about 36 nanoamps. If we deposit a slightly lower water, smaller water thickness, about 4 monolayers, and irradiate at a significantly higher beam flux, we see still the same behavior, where here I've separated out the two species. In the left, we have the water group ions. On the right, we have the substrate ions. And again, we can see that the water group ions pass through a maximum just as the substrate ions are growing in and then subsequently decay with first order desorption kinetics. Interestingly, we do see that the deuterated species decay more rapidly than the hydrated species. This makes sense because we're removing the deposited D2O from the surface and irradiating with the H+. And so we are basically supplying H+ to the system or hydrogen to the system and depleting it of the deuterium.
Hey, Micah,
Yes.
could I ask a question? So, the fact that the intensity increases, does that mean like, because I'm not used to interpreting these kind of plots, but does that mean that it's easier to get does that mean it's easier to sputter something that's right at the silicate water interface than
Yeah,
it is
great.
to sputter something that has a lot of layers of water beneath it? Is that the right way to
Yeah, that's a great
interpret this?
question, Parvati. And so the way that we interpret this is not a total sputtering yield, right? This is the secondary ion sputtering yield. And so what my interpretation of these peaks are is that as the substrate is exposed, you're sputtering basically the interfacial layer between the water and the silicate. And so what we're seeing here is an indication that there's some sort of electronic transfer interaction at that interfacial layer that facilitates the formation of a secondary ion. This doesn't necessarily mean that the total sputtering yields are changing, just that the relative abundance of secondary ions is changing at that interfacial region.
Okay, gotcha. Thanks.
Does that make sense?
Yep.
Yeah. And so there's still a lot of work to be done to understand some of these dips. This might actually be due to the topography of the sample. It might be due to charging. Maybe there's a little bit of charging of the sample that's changing some of these curves. But what we do see in all of the spectra that we take is they do pass through this maximum right as these substrate ions are growing in at their maximum rate. And so the assumption is that is entirely due to the electron transfer dynamics at that interfacial layer between the silicate substrate and the overlying water. Interestingly, when we look at the room temperature spectra before and after the water deposition and the cooling, we again see differences in the sputtered secondary ion spectra. So what I'm showing here is a normalized intensity for a couple of pre-dosing room temperature spectra. I went ahead and included again the dosed sputtered spectra of for the cooled sample, and then the room temperature spectra after depositing the water and then rewarming to room temperature such that any of that adsorbed molecular water can then desorb, and you're left with only sort of that topmost monolayer. When we look at the relative abundance of the deuterated species in the room temperature spectra before and after that dosing event, we see that the relative abundance of those deuterated species is significantly increased compared to the room temperature spectra taken before the sample was exposed to the D2O. So what this is telling us is that for the exposure of our sample to the deuterium, we form permanent SiD bonds or SiOD bonds in that substrate that persist even after rewarming the sample to room temperature. And so that there is a dissociative reaction between the D2O and the irradiated surface to form these SiOD bonds. There's still a lot of work that needs to be done to determine if these can form passively. So can you irradiate the surface to create a defect-rich surface and then expose it to D2O to dissociatively absorb that D2O molecule to the surface? or does it require active irradiation in order for these molecules to form? So that's still work that we have left to do. But really interestingly, I think to think about how we can use these secondary ion signals to probe the hydration state of the silicates in the silicate materials. And so depending on the strength of that SiH or that SiD signal, we can get an idea of what is the relative abundance of those deuterated molecules or those hydrated defect species in the regolith samples. So like I said, I also took some data for ilmenite sample. This one was pretty interesting because we see, in addition to ilmenite, which is FeTiO3, in addition to just the Fe and Ti species, which do feature predominantly in our spectra, we also see some trace species in there as well. For example, magnesium, aluminum, calcium. Magnesium is a well-known substitutional species in ilmenite, and so it's not terribly surprising to see the magnesium popping its head in there. And as I'll show you on the next slide, the calcium is not actually a part of the ilmenite structure, but an inclusion in our mineral. Same with the aluminum. It's a representative of trace inclusion species in the natural ilmenite sample that we have. Again, when we compare the room temperature spectra to the freshly dosed spectra, we see that we can completely cover that ilmenite substrate. So we see only water group ions coming off. That's in the black curve here, where we see only these N equals 1 and these N equals 2 water clusters, a few of these N equal 3 water clusters. And then after irradiating the sample for an hour or so, we expose the underlying substrate. We see those metal group ions grow in. Some small fraction of water group ions still exist, but we see pretty much just the same spectra that we saw in those room temperature SIMs. So again, we can see that there are reactions in between some of those substrate elemental species and the overlying water, where in particular here we can see it for iron, where in the room temperature spectra we see both Fe and FeH. Then after deposition and irradiation, we see that FeH signal is strongly suppressed, and we're seeing almost exclusively the formation or basically a 1-to-1 ratio of the formation of FeD plus. So this is indicating that the deposited water molecules are interacting with the substrate iron. We don't see much of a change in the titanium signal or really any of these other species, suggesting that the water is preferentially interacting with the iron species as opposed to these other substrate cations. So we see, yeah, the relative abundance of that deuterated, that FeD plus, is significantly enhanced after the D2O exposure. Because I didn't expect to see a lot of these other metal ions in here, we did take a couple of quick XRF spectra of this ilmenite sample. These spectra were taken at Georgia Institute of Technology. So this is our big ilmenite sample here. We scanned over a couple of areas in a about 3 millimeter by 3 millimeter block squares. And we see that there is a bit of compositional variation in our sample, where the pink here is the more or less pure ilmenite, and then the bluer sections here are where we're seeing these inclusions of this calcium-rich material. So we have predominantly ilmenite with a few of these inclusions of calcium and aluminum-containing materials, which then lend themselves to the production of the SIM spectra that we just saw. And so the reason, if I just go back here real quick, the reason that we see these minor species, so there's not a lot of magnesium or aluminum or calcium in our sample, but the reason we see them in such large abundances is something I'll talk about here in a minute, is because they have lower ionization potentials. And so this is getting to the fact that the secondary ion spectra are dependent on the ionization potential of the elemental species. So species like magnesium, like calcium, that are relatively easier to ionize are going to show up with a relatively larger secondary ion signal than something with a higher ionization energy like silicon or iron. And so there's sort of a competing effect here where your sputtered signal is going to depend on what is the elemental abundance of that species in your target, but also on what is the elemental ionization potential of that metal species. And so we were able to see, like I said, these verify that these exist from the XRF. We can then get what is the elemental abundance and then use that to determine what is the probability of getting a sputtered secondary ion compared to the sputtered neutral. And I'll talk about that a little bit more in a second. But first, I wanted to just say again, when we do the sputtering as a function of fluence for the ilmenite sample, we see again that water group ion passes through a maximum as the substrate species are exposed. But for the ilmenite, when we compare the room temperature spectra before and after deposition, we don't actually see that a lot of that chemistry sticks around. We see that for the room temperature spectra, the FEH and the FED ion abundances don't change much before and after the exposure at room temperature. And so this is suggesting that for the ilmenite sample, whatever chemistry is happening that causes the FED plus to form more readily when the water's on there, that is not persisting after the water has been desorbed due to warming it to room temperature again. So that's just kind of showing that, we are able to use this technique to detect water from these covered regolith grains. But a few of the open questions that we have is how do we determine what the flux of these sputtered secondary ions is on the lunar surface? And this flux is predominantly going to depend on what is the incident solar wind flux. So how many solar wind ions are available to produce sputtered secondary ions? What are these elemental sputtering yields? And so how many sputtered species are produced per incident solar wind ion? And then what is the ionization probability of that element to determine all of the sputtered secondaries, including the neutrals and the ions, how many of those are actually ions? Additionally, the secondary ion spectra can depend on the mineral composition and the crystallinity of the sample. These are open questions that we are not really getting at with this work, but we have some ideas out there to continue it and to better determine how mineral composition and crystallinity is going to affect that secondary ion signal. Additionally, the secondary ion signal can depend on the type and energy of incident ion. And so we want to be able to measure the secondary ion spectra for both incident hydrogen and incident helium, maybe do some incident oxygen atoms and look at how those secondary ion spectra change as a function of the incident ion. And then finally, the yields, it should vary depending on the temperature and the volatile concentration on our mineral samples. And so that's another thing that we want to look at is, by varying the temperature, how do we change the total yields and the relative yields of the sputtered secondary ions. One caveat to this technique is that it does produce overlapping ion masses. For example, CaO overlaps with Fe. And this can make the signal interpretation a bit difficult. in trying to determine how much my signal is due to an oxidized or a molecular ion versus an elemental ion. And so we've been working with some folks here at Goddard to look into the possibility of using machine learning to extract what is the actual substrate composition based on a secondary ion spectra. And you'll see why that's important here in a second. So to get at this first part, though, the flux of secondary ions leaving the lunar surface, the first thing that we want to know is what are the sputtering yields? How many of these secondary species are being removed as a function of that incident solar wind? And so the way that these simulations are typically done is we use Monte Carlo codes such as SRAM or SD-TRIM-SP, where we assume simulate the implantation and energy loss of incident ions into a given substrate. And then by repeating these simulations thousands of times, we can extract what are then the average sputtering yields. So how many sputtered secondary species are produced per incident ion. These techniques are pretty rapid. These Monte Carlo simulations can run quickly. They are based on empirical interatomic potentials. And the sputtering yields depend sensitively on the surface binding energies of a given species. And so this is something that a lot of folks have been working on in MD simulations to better understand what are these surface binding energies for a given elemental species in a crystalline matrix. And so a lot of work is going on in that, but we use these empirical potentials to then estimate what would then the sputtering yields be. Important to note is that these Monte Carlo simulations do not account for the target crystallinity, for target roughness, for any chemical reactions or electronic excitations. But when we compare the yields calculated by these Monte Carlo simulations to experimental data, we do get pretty good yields. And so we can determine that these parameters are not affecting our yields substantially enough to totally throw off our simulations. We can impact these simulated ions into, here I'm showing the impacts of a 1 keV H plus into an anorthite composition. And so we see that depending on the chosen surface binding energy of oxygen, you can get very different sputtering behaviors as a function of that incident ion fluence. And so we see that assuming a relatively low surface binding energy for oxygen, we actually deplete oxygen from the surface. And so this is the surface compositional ratio for this anorthite. It's originally about 0.6 or 60% of oxygen. But as we sputter it at these low binding energies, we see the oxygen is depleted, and the other species, including I guess I've left off the legend here, my apologies, but the aluminum and the calcium, and so this is I believe aluminum, silicon, aluminum, and calcium from that anorthite sample. We see that those are relatively enhanced, or the relative abundance is increased at the surface. However, if we assume a slightly higher oxygen surface binding energy, and this is more similar to what people are finding is appropriate for mineral species, there is not that much preferential sputtering. There's a little bit of a decrease in the amount of oxygen on the surface, slight changes in the relative abundances of the silicon and the aluminum, but more or less at these higher binding energies, there's not this really strong evidence for preferential sputtering of species from these Monte Carlo simulations. We can look at how these change. The elemental sputtering yields change as a function of the oxygen binding energies. And so we see, assuming a static condition or even a dynamic condition with a fairly low oxygen surface binding energy, you're getting pretty high sputtering yields. And so this is 10 to the minus 3 atoms per ion. So about 0.06 for the static case, about 0.02 for the dynamic case. But when we dial up that oxygen surface binding energy to more realistic values for minerals, we see that that drops to about 0.01 sputtered secondary ions, or I'm sorry, sputtered secondary species per incident ion. But it's important to note that the sputtered secondary ion yields do not match the elemental sputtering ion yields. And the way that I want to talk about this is by looking at some SIMS spectra that we measured for a series of Apollo lunar samples. And so I'm showing here Apollo lunar sample 65901. This is a very mature sample, average grain size about 85 microns. And this was irradiated using several different incident ions, 2 keVH plus, 4 keVHE plus. And the composition of this sample was measured in situ using X-ray photoelectron spectroscopy. So we're able to both measure the surface composition using XPS and the secondary ion spectra using SIMS. And so we want to know, how do the sputtered secondary ion spectra compare to the actual composition of that lunar soil? And this is where I was talking about earlier, is it gets pretty confusing when you start accounting for all of the different metal species and potential molecular ions that can form in a complex mixture such as the lunar regolith. And so for the ion incident ions that I'm showing here, we do see all of these major elemental species in that secondary ion spectra. So the aluminum, the silicon, the calcium, the iron, the titanium, all of those are present in that secondary ion spectra. So we know that we're looking at lunar soil, but there's a lot of overlap between the different isotopes and the molecular ions. And so the way that we account for this in our modeling is to use what's called a relative secondary ion yield. And the relative secondary ion yield is just defined as the ratio of the secondary ion intensity for a given species compared to silicon, multiplied by the relative composition of silicon to whatever that ion species is. And so this tells us, you know, if we see a high ion signal for, say, potassium, which has a relatively low abundance in our sample, this has a high relative secondary ion yield. We see that that secondary ion yield, that relative secondary ion yield, is roughly proportional to then the elemental ionization energy. So species that are easily ionized, like potassium and sodium, calcium, those have a relatively high secondary ion yields compared to, for example, silicon, which everything is ratioed to here. We can see that when we compare the relative secondary ion yields for a number of different lunar soils and a few lunar regolith analogs, there's quite a bit of scatter. And that scatter is indicative of the uncertainty in the position or the you know, what is the crystallographic position of these cations, and then how do the relative yields change as a function of the different incident ions. And so there's still a lot of work to be done here to better constrain these relative secondary ion yields so that we can use a measured SIMS spectra to truly understand what is the composition of the underlying surface. And this is where I think that the machine learning could come in a bit handy, is that it could help us understand better for a given secondary ion signal what is then the true composition, the underlying composition. But on the whole, the secondary ion, the sputtered secondary ion yield is about 0.02 to 0.01 ions per ion for silicon, and then that's going to increase, you know, based on the relative abundance of the sample. It is going to, you know, you're going to see all of these other species as well. So when we put together these experimental measurements together with the estimated fluxes of sputtered secondaries coming from the binary collision or the Monte Carlo approximations, we can estimate what are the surface elemental fluxes, so the total fluxes of a given species leaving the surface. And then by applying that relative secondary ion yield, determine what are the sputtered secondary ion fluxes coming from the lunar surface. And so the blue bars here are showing the total yields determined from the SD-TRIM SP simulations. And we see that we get a lot of oxygen, a lot of silicon. That's what we would expect. Those are the most abundant species. And the yields are sitting at about 10 to the 4 to 10 to the 5 sputtered atoms per centimeter squared per second for typical solar wind fluxes on the lunar surface. When we apply that relative ion correction for the secondary ions, we see that the relative abundances of these species changes significantly. We don't see any oxygen, mostly because oxygen doesn't form as a positive ion, and we're talking about the positive secondary ion fluxes here. If we're looking at negative secondary ions, we would see some oxygen, but it's predominantly formed as a negative ion, and we just have the positives here. But we do see that the relative abundances of things like silicon are decreased, while the relative abundances of calcium, potassium are increased compared to their total abundances. And what we don't have yet are really good estimates for what are the yields of water. From the secondary ion spectra that I showed of the water deposited mineral samples earlier, we can estimate that the yields of water are about 10 times lower than the peak ion fluxes for the pure water samples, meaning that for water deposited onto a lunar sample, if we're seeing about 10 to the 4 aluminum ions per centimeter squared per second, we would expect to see about 10 to the 3 water ions per centimeter squared per second. So we're getting about 1,000 water molecules sputtered from the lunar regolith per centimeter squared per second. So we think that that can produce a pretty observable signal on the lunar surface if there is appreciable water around. I do want to mention that this is not only a technique that is applicable to the lunar surface. We've also done some work looking at solar wind sputtering from Phobos and Deimos, which are the moons of Mars. They're exposed to both the solar wind and Mars magnetospheric oxygen ions. And so we were asking the question, if you sputter the surfaces of Phobos and Deimos, are you producing enough secondary ions to then be detected by an orbiting spacecraft around those bodies? In order to determine what are the fluxes of ions around Phobos and Deimos, we first needed to measure the sputtered secondary ion energy distribution. So that's going to control how fast these ions are leaving the surface before they're picked up in the solar wind. So when we look at the, you focus mostly on the right here, the predicted Sigmund-Thompson energy distributions for sputtered species versus the SRIM calculations of those energy distributions, we see that when we measure the actual secondary ion energy distributions, they peak at a much higher energy, around 10 eV, almost an order of magnitude higher than you would expect for the sputtered neutrals. Now, this is again indicative of some energetic charge transfer processes going on at the surface that cause these ions to leave at a slightly higher energy than sputtered neutrals will. But from these sort of 10 eV ejection energies for the secondary ions, we can then determine what are the ion trajectories and the densities around different airless bodies. And so what we're showing here is a series of Monte Carlo trajectory calculations for solar wind sputtered secondary ions around, on the right here, about a 10-kilometer sized body, and on the left here, a lunar sized body. Now, so what we see is that using these sputtered secondary ion trajectory calculations, for a small body, we get more or less a cloud, because you can, the scale heights are similar in the two cases, but for the smaller bodies, the gyro radii are larger than the body diameter. And so ions emitted from just about anywhere on the surface are able to be detected if you can get in close orbit. Whereas for something like the moon, because the gyro radii of the emitted secondary ions are smaller than the lunar radii, any ions ejected from the minus B hemisphere are going to be re-impacted into the surface, whereas anything ejected from the positive Z hemisphere is going to be rapidly beamed. And so all this is saying is that for orbital measurements, it's unlikely that you would be able to make SIMS measurements in orbit around the moon because of this beaming effect. Whereas if you were close to a small body, you could basically fly through a cloud of these secondary ions for the vast majority of your orbit. Now, this is not going to affect the lunar surface measurements that much because you're going to be even better scenario than you would be in these small body situations where you can get right up close to the surface within centimeters if you really want to, and be able to collect those sputtered secondary ions basically all the time. So just finishing up here, we can also use the relative abundances of these secondary ions to do some very first order origins calculations. And so looking at the ratio of iron to silicon versus magnesium to silicon, you can see there's a pretty clear separation between primitive bodies such as chondrites versus evolved compositions. And then by comparing this for a couple of different elemental pairs, calcium, silicon versus magnesium and silicon, we can start making some assumptions on if we go to a small body and we measure, these ratios, we can expect it to be either a primitive or an evolved composition. And I just want to finish up by mentioning that the first attempt to make these kinds of measurements is going to be carried out by the MMX mission, which is a JAXA mission to Phobos and Deimos, where they are going to be flying this spacecraft around Phobos, measuring the sputtered secondary ions, and then they'll actually land on the surface and return a surface sample of Phobos to the Earth for compositional analysis. And so we'll be able to test a lot of these theories directly after the completion of this mission. So in conclusion, the solar wind sputtering of silicate regolith grains and ice-colored analogs produces secondary ions that are readily detected by a SIMS instrument. And you can do this with very low backgrounds of contaminant species and high fidelity, meaning that you can get high throughput and very high fidelity measurements of these sputtered secondaries. The abundances of these sputtered secondary ions can then be used to infer the surface composition of these airless bodies, and presence of certain secondary ions can be used to prospect for valuable resources. And based on the work that we've done here, we think that SIMS sensitivity is potentially high enough to detect even trace amounts of water that is adsorbed onto the surface of regolith grains on the moon. There's a lot of work left to be done to determine whether SIMS sensitivity is to the volatile abundance, the underlying substrate composition, morphology, temperature, but we're really excited about where the work's at and excited to keep it going. So happy to take any questions.
Awesome. Thanks, Micah. We lost a couple of people, but it was a really good talk. And if anyone has to drop off right at the hour, you can email Micah later. But
yeah, it took way too long.
But it was all good stuff. So don't worry about it. But yeah, we have time for maybe one or two quick questions. I guess one from Michael Poston, which I'll read out of the chat, which I was also wondering, has Artemis, like all caps Artemis, detected surface sourced ions, like secondary ions?
So they've detected the pickup ions. Yeah. And so the pickup ions are substantially higher energy, hundreds of eV. And they did make these chance fly-throughs of the plume, right, of pickup ions. What you can't say from those measurements is whether or not you're measuring sputtered secondaries or photoionized pickup ions. Okay. And so they're able to measure ions which definitely come from the lunar surface, but you don't know if they're sputtered secondaries or photoionized neutrals. You can't back calculate to where those came from on the surface. but certainly they have measured surface sourced ions. No one, to my knowledge, has ever done these secondary ion measurements, though, where you're directly looking at these lower energy sputtered secondaries.
Okay, cool.
So
More questions? Yeah, go
will
ahead,
the
Michael.
Mars one be able to tell the difference?
Yeah, so that's what's really cool about the MMX mass spec is that they'll have basically they'll be able to just turn off their ionizer and measure any secondaries that are coming off of the body, and they'll be close enough to get to the sort of in that sputtered secondary ion cloud, and so they'll be able to distinguish pickup ions at these low energies from the the sputtered secondaries at the low energies from any pickup ions.
Oh, right, because Mars moons are basically small bodies that got captured.
Yeah, they're about 10 kilometers, so they're pretty small. And so a lot of these secondary ions, they don't even have a chance to get very picked up by the time they reach the spacecraft. Spacecraft's, I think, primary science orbit is about 15 to 20 kilometers. And so they'll be, within a body diameter or so of Phobos and Deimos. And there just won't be enough pickup to really change those energy distributions. And the MMX instrument should be sensitive to those lower energy ions.
Okay, any final questions, Paul, Cynthia, maybe?
I have maybe a brief question. Micah, really cool talk.
Thanks.
You mentioned briefly like negative ions for oxygen.
Yeah.
Would you expect any like water clusters to emit these negative ions? Because I mean, the Chang'e 6, I think, now had a negative ion instrument on board from Sweden. And I don't think they've written a paper yet, or maybe they have. Not fully up to date on that. But could this help maybe like clean up the spectra a little bit, so to say?
I believe so. So I haven't taken any negative ion data for water. I think there is some data out there that show you do for water you get a lot of these positive ion clusters, but for a bare silicate you get a lot of O- and OH-. And so I think that they would be, those negative ions would be readily detectable. It's still, I'm not sure exactly what it's going to look like for silicates, though.
Thank you.
Mm-hmm.
Cool. All right. So we're a little over the hour, so I think we'll wrap it up. But thanks, Micah, for sharing the stuff with us. Like it's
Yeah, thanks
cool
all
work,
for
and
tuning in.
yeah, look forward to seeing how it evolves.
All right.
All right. Thanks for calling in, everyone. Take care. Happy Thanksgiving in advance.
See ya.
Bye.